Welcome to everybody. Welcome to this fifth session of the Foundations of Computational Mathematics online seminar series. So I'm your chair for today. I'm Ben Adcock from Simon Fraser University. We have two excellent speakers today. The first is Philippe Groh from Vienna, and the second is Sara van der Geer from ETH Zurich. Before I introduce our first speaker, I just wanted to briefly review the procedures. So as you can see, we have the chat open for the participants. Please feel free to post questions in there and I'll monitor it during the seminar. If you wish to ask a question, you can also raise your hand and then I can unmute you to ask your question. We'll also have a question session at the end of each talk as well. Just a reminder, as you can probably see, we're live streaming the seminar on YouTube and the recording of it will be available afterwards there as well. Okay, so without further ado, let me introduce our first speaker. So our first speaker today is Philippe Groh. Philippe is a professor in the Faculty of Mathematics at the University of Vienna, where he is also head of the Research Network in Data Science. His research interests include approximation theory and computational harmonic analysis, numerical methods for PDEs, and most recently, machine learning and deep neural networks. He's won various prizes for his work, including most recently the 2020 Alexander von Humboldt Professorship. He's also a member of several editorial boards, including Constructive Approximation and IEEE Transactions on Information Theory. So we're delighted to have him today as our first speaker in the FoCM seminar series. Today, he's going to talk about deep learning in numerical analysis. So please, take it away.
Okay, so thanks a lot, Ben, for this very kind introduction. I would also like to start by thanking Albert, Markus, and Ben for putting together this seminar series. So I appreciate this very much, and it's a big honor to be able to present here. So my talk will be about deep learning in numerical analysis. And before I start, I would like to give a shout out to my great collaborators with whom this work would not have been possible. So first, Felix Voigtländer, Philippe Marketant, Raphael Reisenhofer, Leon Gerard, Michael Scherbala, and Julius Berner, all at the University of Vienna, who collaborated with various things that I will present today. So, okay, I mean, as we all know, deep learning has changed the things that computers can achieve and has been in the news very frequently with major successes in playing Go or machine translation, and also in the natural sciences, for example, protein folding. And basically, I will talk today about applying these methods in the context of numerical analysis and how these methods can be analyzed. So mathematically, as most of you probably know, deep learning is basically solving a regression problem with neural networks. So fitting a neural network to point samples. Yeah. And just to get down the definition right in the beginning of neural networks. So these are a parametrized class of functions. The parameters are matrices and vectors. And basically the way a neural network computes its output from an input x1, x2, x3, for example, is to propagate this input across layers. And in each layer, the operation that is applied is an affine mapping followed by a pointwise nonlinearity. And this is repeated over and over again for a certain number of layers, and then you get the output. So you would fix an architecture, which describes the number of nodes which are in each layers. You fix a maximum layer size and an activation function. And in this talk, I will exclusively focus on the probably most popular activation function, which is the rectified linear unit. So it's a piecewise linear function, which is the identity for positive x and 0 for non-positive x. And then I'm just, so this just denotes the procedure that I just described in words. So the parameters are these matrix vector pairs, which compute the propagation from one layer to the next, followed by an activation function. And the output of the neural network, so the function that is associated with it, so the realization, is denoted by phi of x, and theta denotes the parameters. And for later use, we will also define hypothesis classes. So typically one would fix an architecture, so basically the network size, and maybe some bound on the coefficients. And this gives us a so-called hypothesis class. Okay, so then once we have fixed this, the typical flow chart in supervised learning is that we get some data, xi, yi, so we get m many data points. And basically we fix a neural network architecture, and we try to minimize a loss, and this loss is typically a function that uses point evaluations of the neural network, or also gradients maybe, and the labels, and it somehow computes a proximity between the predictions of the network and the labels. And the neural network is trained, so the algorithm that usually fits such a network tries to minimize this loss. So it tries to find the parameter theta that minimizes this loss function via stochastic gradient descent methods. And the hope is, once we have done this, that in some way the neural network that we found represents our data well. In statistical learning, typically one assumes that the data comes from some probability distribution and, for example, consists of IID samples. And then we would like that the neural network not only makes this loss small, but also the true expected loss with respect to the distribution, right? So that's what is typically analyzed within statistical learning. So in common applications, you would have, for example, a bunch of images, which I would like to classify according to what is on them. You have maybe a sophisticated neural network architecture, which incorporates invariances of your problem. You might have a Kullback-Leibler divergence, for example, if this network should represent classes to which the objects on the image belong, and then you can train this with our flowchart. And here, what we hope to get in the end is just a good classifier. So if you put in an unseen image, it should output what is on the image. I mean, these are successful applications. So, I mean, initially breakthroughs happened in image processing and in image classification problems, but more recently, these methods have also been applied to solving PDEs. And I would just like to mention maybe, so one of the first works was by Hahn, Jensen, and Wayne Ö. And another contribution was by Raisi, Piadikaris, and Karniadakis. And the latter approach basically takes a PDE. I'm just now here writing a simple first order PDE, which is stated on a domain and satisfies boundary conditions. And basically you can cook up the same scheme as before, meaning you now generate training data yourself. So you sample points in your domain, you sample points on the boundary, you devise a loss. The loss in this case of pins is often just the residual of your PDE with boundary conditions. And basically you do the same thing as before. And well, what you now hope is to get a PDE solution. And as a numerical analyst, naturally there are two questions that one typically asks in this context. So, well, first of all, an approximation question. So I want to approximate a function, in this case a PDE. So this is typically an object that one can get a good handle on mathematically. And I would like to ask if I prescribe an accuracy, how large do I have to choose my architecture such that there exists a neural network in this architecture that achieves error epsilon. And in particular, the scaling between the accuracy and the size is a quantity of interest in approximation theory. But of course, this is only part of the story. So of course, we would also like to know to which extent, if I know, for example, if I want to have accuracy epsilon, I need so and so many nodes in my neural network. How can I find these nodes? And in particular, is it possible to find an algorithm, particularly the algorithm that from the deep learning flowchart, which realizes this approximation rate? So these are two questions that I would like to address in this talk. And first, I'm going to talk about approximation. So the general question is, I have a function u, and I want to ask if I prescribe an accuracy epsilon, how large do I have to choose my network architecture? And I'm just going to mention some results in this direction. And actually, I'm just going to mention some kind of a meta result, which states that basically if you just measure performance in terms of approximation power, then neural networks are, well, at least as good as all classical other methods. So roughly speaking, this means that if you have some approximation method, think of polynomials, finite elements, wavelets, low rank approximation, frame methods, sparse grids. So whatever your favorite method is, and assume that you know that using n degrees of freedom in this method, you can approximate a function to within accuracy epsilon, then there exists also a neural network that almost realizes the same approximation rate. So you can then find a neural network that has approximately the same size as the degrees of freedom from your method and that achieves the same error. And the proof of this is basically you kind of rewrite these methods in terms of neural networks. And this has been carried out for now like a lot of methods. So the approximation is at least as good as all classical methods combined, and it's actually even better. So one can show, for example, that you can also approximate fractals with exponential convergence, so which is completely impossible with classical methods. You can approximate oscillatory textures with exponential convergence, and the convergence, so the implicit constant, only logarithmically depends on the wave number. And you can also approximate piecewise smooth functions with an optimal rate. And these are all things where really classical methods struggle. So I mean, the approximation capabilities are really great. And I would also like to mention high dimensional functions, which is something that comes up in many challenging applications in numerics. For example, when we want to solve PDEs, in option pricing, the Black-Scholes PDE is typically a high dimensional PDE that we would like to solve. Optimal control problems with a high dimensional state space gives rise to Hamilton-Jacobi-Bellman equations. And last but not least, another high dimensional PDE is the multi-electron Schrödinger equation, which computes wave functions of ground states. And again, if I have a molecule, the dimensionality of this ground state is 3 times the number of electrons. So this can be rather large. And it's a big challenge to solve these problems actually numerically. And there are many reasons, and probably the main reason is that the curse of dimensionality. So most methods, when they try to scale up to high dimensions, their runtime or their computational complexity scales exponentially in the dimension. And if the dimension is, let's say, 50 or 100, that's a big problem, right? So it's really an unsolved problem in general to accurately solve the multi-electron Schrödinger equation or certain nonlinear Hamilton-Jacobi-Bellman equations. And well, in addition to the high dimensionality, they also have some structural properties like non-smoothness and things like that, which make it quite challenging. So quite surprisingly, also neural networks, in addition to what I just said before, are also capable of approximating solutions to at least Black-Scholes PDEs and certain Hamilton-Jacobi-Bellman PDEs without incurring the curse of dimensionality. So in terms of approximation, they are really an excellent model class if the goal is to approximate complicated high-dimensional functions. So just to recap, one can prove basically that this one class achieves very good approximation and optimal approximation for smooth functions, for all classical function spaces, for fractals, and also for high-dimensional functions. And I mean, this sounds really, really good. And of course, the question is, well, I mean, is there a catch to this? And I mean, if we think about it, the catch could be whether these approximation rates can actually be realized by an algorithm. So can we find these neural networks? And this is the question that I would like to address in this part. Can these approximation rates be realized by an algorithm? And actually there is some evidence, some experimental evidence by our chair, Ben Adcock and Nick Dexter. And so they really performed a very thorough numerical analysis of deep neural network approximation. And one of their main findings was that it is highlighted here that there seems to be a gap between the approximation theory, so the theoretically postulated rates, and the practical performance with trained DNNs. Yeah. So it happens that you have a function for which you can prove high approximation rates, but if you try to run with SGD and train it, then you will get a much lower rate and much poorer performance. And so the question is, can we analyze this problem mathematically? Can we design better algorithms which actually harness the approximation rate? Which okay. So in order to ask this question in a rigorous way, one can go to the field of information-based complexity and rather classical concepts such as Gelfand numbers, sampling numbers. And I'm just going to give a quick run through this kind of theory. So suppose, as we have in deep learning, suppose that we want to learn a function or approximate the function using an algorithm. This algorithm is called A of U, and U is the unknown function. Okay, so what do we know about this function U? Well, the first thing that we get are samples, right? So for example, in the PDE example, we got samples of U or its gradient and xi's, and these can be random samples, this can be chosen adaptively, it doesn't really matter. And from these samples, we would like to estimate U. Of course, this is impossible because if we don't have any additional information, then any function interpolating the samples will be a good guess. And I mean, there are many of those. So we have to add some model information. And this model information can be somehow incorporated in terms of regularization or a smoothness condition. For example, if my function solves a PDE, I know that it is smooth, right? And of course, this restricts then the class of functions which can interpolate this data. In our case, this model information somehow has to correspond to neural networks because we try to do deep learning. And then we can ask ourselves, how well does this algorithm perform? So I have my model information, I have my samples, and I have my algorithm, and now I'm asking, well, how big is the error of this algorithm over the entirety of my model class? So I want my algorithm not only to work on one particular element in my model class, right? So this would be very unsafe. So I want to work it. I want it to work on all elements. Yeah, and there are some key quantities that describe the behavior of such algorithms. Okay, so first, let me define the sampling number. The sampling number beta MP of my model class U is just this error here with respect to the LP norm, but it's actually the infimum of all algorithms that I could possibly have, that I could possibly think of this error. So this is really the theoretical benchmark, right, that I could possibly obtain. We don't assume anything about this algorithm in the sense of being efficiently computable. So that's really a benchmark. So if this is large, then there is no hope of getting an algorithm based on M samples that gives us a good error. And then we are interested in asymptotics. So what is the scaling between the number of samples and the error? And the optimal such scaling is what I call here the optimal rate. So it's the best gamma, the biggest gamma, such that the sampling numbers decay at a polynomial rate gamma. Okay. And of course, I mean, the sampling number also gives a lower bound on all possible algorithms with runtime scaling with M, because reading every sample takes a minimum amount of time. So this is really a bound on the best error that I could get for any algorithm that has a runtime scaling with M. Okay, and likewise for this optimal rate. So this is a general theory, and all these quantities are quite well understood in like classical function spaces, but we would like to relate them to deep learning. So what is the kind of model information that we would like to use here? Well, for sure, we would like to use the fact that our function can be well approximated by neural networks, right? Otherwise, I mean, the whole approach wouldn't make much sense. So our minimal information is that our model class is contained in the neural network space, ULC alpha. And this is just a space of functions which can be approximated at a rate n to the minus alpha by neural networks that have size n and that have their architecture somehow constrained by L, and their coefficients have to be bounded by C of n. Okay, so that's kind of the minimal information that I would like to ask from my model. And second, in the other direction, I would like that I really have a deep learning problem. So what does it mean? I really have some free network parameters that I would like to fit. Otherwise, and this is ensured by the following conditions. So I also want to have that at least my model class contains a copy of a small neural network. Let's say with 2 hidden layers, and the output layer is 1, the other is 2, and here I have an n, so this can be arbitrary. So I want to have at least like a very small neural network contained in U, which kind of means I really have to fit some network parameters. So what does it mean that a theoretical approximation rate cannot be realized computationally? Well, if my optimal rate is, this should be less than alpha and not less than or equal alpha, okay? This is less than alpha. So if this optimal rate is really less than alpha, then the number of samples that I need in order to get a prescribed approximation error scales worse than the theoretically possible rate. So then this means that the approximation rate cannot be realized by any algorithm, including stochastic gradient descent, but there doesn't exist any other algorithm either. In particular, more or less, what this optimal exponent means is that the runtime to get an LP error less than or equal epsilon scales at least like epsilon to the minus gamma. Yeah. So this gives a lower bound on the runtime. And in particular, if this optimal exponent is like scales like 1 over the input dimension, then any algorithm suffers from the curse of dimensionality. Yeah. So because if I have here 1 over d, then this would be like epsilon to the minus d. And this means that the computational runtime scales exponentially in the dimension. Right? Okay. So what we did was compute optimal rates for neural network spaces. Okay. And let me now show some results that we could achieve in this direction. And before I would like to stop because this is kind of a loaded slide. So is everything clear so far? Okay. First result. So let's fix some notation. So this L infinity just means the maximum depth of my approximating network. The C of n, it scales more or less polynomially in n with some exponent. Okay, and from this we define a parameter tau, and this is alpha. Alpha is the approximation rate in my neural network space, and this quantity here. So the important thing is only that this is an explicit parameter, and it is always less than or equal 1. Okay. So now the first result that we show is that the optimal exponent, so for any neural network approximation space, is equal to tau divided by d. If I restrict my neural networks, my approximating neural networks, to have a bounded depth. Otherwise, it's 0. Okay, so we compute this exactly. And in particular, what this shows is that if I try to conceive any algorithm that performs uniform approximation on these approximation spaces, the algorithm will actually suffer from the curse of dimensionality because the optimal rate is less than or equal 1 over d. And this is even true if we can prove that theoretically there exists an approximation that does not suffer from the curse of dimensionality. Well, if we want to compute it, we get the curse back. Second, if the rate of layers, of network layers, can grow as if we make our approximating networks deeper and deeper as the accuracy increases, then one can show that no positive convergence rate can be realized at all. So basically, the convergence can be arbitrarily small. And that is even if we can show that there exists an approximating network of an arbitrary approximation rate. So that's really quite a gap between approximation and realizability. So we also analyzed approximation with respect to the L2 norm. And here we also have quite sharp bounds on this optimal exponent. So this time it's it's somehow caught in an interval, and this interval goes to 1/2 basically if alpha goes to infinity. And again, what we see is by utilizing the fact that this tau is always less than or equal 1, that also for L2 approximation, there does not exist an algorithm that achieves a convergence rate better than 3/2. Okay. On the other hand, one can prove that there exist algorithms that achieve a small rate, about 1/2, and this is independent of the dimension. So L2 approximation can at least in theory be achieved without curse of dimensionality. But the high rate will in general not be possible. Okay. But this does not, so the existence of algorithms, of course, does not imply the existence of efficient algorithms. That's a big open problem. Okay. And I would also like to kind of to say that this is kind of a peculiar phenomenon. So if we now replace these neural networks, these approximation spaces, by linear spaces, yeah, so these sigma n's now are not neural networks, but they are now linear spaces. And I can likewise compute or define approximation spaces, roughly speaking, all functions that have an approximation at n to the minus alpha. Yeah, if these are finite elements or polynomials, this would be a Sobolev space or a Bezov ball. Yeah. And one can actually show, and it has been shown in very nice and recent work by Albert and Dolbeau, that, well, any such approximation rate can be realized from point samples. So in any linear approximation method, there is no theory to break this gap. So this is really something that is quite peculiar and special to this type of approximation. Okay. So this is the first set of results. Are there any questions about it, or can I just go to the next? So maybe one can say that, well, instead, we don't need our algorithms to work on all functions that are well approximable. Maybe we can just pick a more restrictive model class by regularizing. Now here we have the following result, that if my model class contains a copy of a small neural network, so it has input dimension d, the first layer has n nodes, the second has 2, and the output layer 1, and all coefficients are bounded by some constant. Then what I can do is I can divide n by 4 and get s, and then the optimal rate again is always less than or equal 1/p. So that's the error norm plus 1/s. So this means basically that as long as there is some small, so there it's really a neural network coefficient fitting problem. So if I have a copy of a small network in my hypothesis class, then every algorithm has a runtime that scales like epsilon to the minus 1/p plus 1 in order to achieve an LP error less than or equal epsilon. And what we see is that even if we choose a very small model class, if we really regularize viciously, then still we cannot get a high order algorithm. Okay. And if my model class contains a copy of such a network architecture where the first hidden layer has proportionally to the input dimension many nodes, then every algorithm will suffer from the curse of dimensionality if we try to get, if we want to control the uniform error. Okay. So, well, okay, I mean, that's how it is. And I should also say that I mean, this assumption that the first hidden layer has d many nodes basically means that these functions are genuinely d-dimensional. So if this has like only much fewer nodes, it basically means that the functions I'm looking at are defined really on a much lower dimensional subspace. Okay. Okay, so these are the main results regarding computational realizability, and we really find that there indeed is a big gap between theory and practice. Now, the proof ideas are kind of well, I mean, it's a I mean, what you do in this business is usually you try to construct very narrow peak functions which just vanish on the sample points, on as many as or on all the sample points, and you try to squeeze as many such peak functions somehow into your hypothesis class. And then one can perform what is called an average case analysis of the error, and this gives us then the upper bounds on the optimal rate. It's, I think, quite remarkable that we can match these upper bounds, so we can also show existence of algorithms, at least for L2 approximation and L infinity approximation. So the L2 approximation bounds, they use classical concepts from statistical learning theory. And in particular, it shows that basically the best thing you can do is just sample the xi's uniformly. This should be a D, and solve an empirical risk minimization problem, which is basically what people do. Yeah. The optimal algorithm for uniform approximation would be to just interpolate on a uniform grid. And showing that this works requires to control the maximal Lipschitz constant of functions here in this class. So that's kind of how the proofs go. Okay. So there are some extensions. So I mean, we can do the same thing if we assume that we not only have samples of U, but also of, let's say, F of U and gradient of U. And so all our hardness results also apply to solving first order PDEs. So the same results hold. Okay, the sampling strategy doesn't help. So we could even sample our points xi adaptively, but the result still holds, and also similar bounds hold if we want to do quadrature, if we want to approximate the integral of a function. So also no high order quadrature rules exist, and basically if you just do standard vanilla Monte Carlo quadrature, that's almost as good as one can do. Okay. And what is quite well, I mean, these are not only theoretical results. I already quoted this very nice work by Ben and Nick. And in their experiments, what you actually see is that if you try to fit a nice and smooth function using ReLU neural networks, so it actually performs quite good, but you will always get these narrow peaks here. And they prevent you from getting a good pointwise estimation. And the deeper your network gets, the sharper these peaks will be. And so this phenomenon will be more pronounced. And that's basically exactly what our proofs also show. And also in the context of image processing, it's very well known that neural networks that are trained are typically very unstable. So there are some perturbations that you can apply, very small perturbations to an input, and the output, the classifier, will be much different. And basically, if you want to put it somehow pointedly, one can say that these hardness results say that there is actually no way to remove this phenomenon if we are using at least the ReLU activation function. Okay. So let me draw some conclusions. So if we use the ReLU activation function and we want to get a small uniform error, then, well, it might not be the best thing to work with neural network regression, because we cannot get a convergence rate better than 1/d. Okay. And also, if we want to have a very high convergence rate and we want to use the ReLU activation function, this is not really possible with algorithms that use samples of U. Okay. On the other hand, they may be very well suited for high-dimensional problems, where we only want to control, let's say, the L2 error. For example, in high-dimensional PDEs, if we think of the Schrödinger equation, what we're really interested is the energy, so a functional of the wave function. So this could be something where these algorithms perform very well. And if we want to have a dimension-independent rate, but a moderate rate. And in many cases, actually, one can prove the existence of such algorithms, but it is still an open problem whether the implementation of these algorithms, whether they can be implemented with a computational runtime that does not suffer from the curse of dimensionality. Okay. But I mean, there are some promising results, numerical results, for example, in solving the high-dimensional Black-Scholes equations, where we see that it looks like actually also the computational complexity of doing stochastic gradient descent, so of solving an empirical risk minimization, only scales polynomially in the dimension, in the input dimension. But it's very hard and completely unclear how to prove this. Well, also, I mean, there is kind of one thing that deep neural networks can do very well is approximate complicated functions with only very few parameters. And this means that once I have found these parameters, I can evaluate the function extremely efficiently, because it only depends on few parameters. And there are actually several problem classes where it happens that it's much more important to evaluate the function than to compute it efficiently. So you can spend a lot of time computing your PDE solution, but what you really want is to evaluate it efficiently. Okay. And this is also something where these algorithms can be very impactful. And finally, I would like to stress that all these results, they depend on the rectified linear unit activation function. So it is not clear to me what happens if we choose other activation functions. And I think that's a very important question, and also other architecture, and in particular to kind of categorize activation functions, architectures, according to this optimal exponent. And I think this will give us an idea of how stable certain architectures are. And so, I mean, I just said that for high-dimensional problems where you only want to control a functional, these methods might be very efficient. And in this last part, I would like to kind of to show an example where this is indeed the case. Okay, and this example is in computational chemistry, namely solving the multi-electron Schrödinger equation. And I'm not going to say too much about the model itself. So basically what we want to do is we want to compute the wave function of the ground state of a molecule. And if we fix the coordinates of the nuclei, we have this electron sitting here, and the wave function basically gives us a probability distribution of where each electron sits. Okay, and we would like to find the configuration that has the least energy, and for this we minimize this energy here, which contains the Hamiltonian that encodes the kinetic energy and the forces between different nuclei and electrons okay. So this is what we want to solve, and that's very challenging. For example, there are some conditions on symmetry. So each electron has a spin, a positive or negative spin, and depending on whether spin coordinates are equal, this wave function has to be anti-symmetric. Okay. So this has to be encoded into the model, and it's usually very high dimensional. And okay, but it's a minimization problem. And what we're really interested in is the ground state energy. So that's the energy of this minimizer. And what we're really interested in is actually the mapping that maps these nuclear, the coordinates of the nuclei, which I will call the geometry, the molecular geometry, to this ground state energy. This is the potential energy surface. And if you compute the gradient of the potential energy surface, you will get a force field, and this will allow you to do molecular dynamics. Okay. So this is a high dimensional problem where only a function of the solution is important. And it would be great to have at least some small dimension dependent convergence rate. And just to show you a picture, actually from our algorithm here, if you have like a hydrogen chain, you can compute this energy surface, and then you can also compute these forces, and then you can do molecular dynamics. Okay. So the one way to solve this Schrödinger equation is using variational Monte Carlo. And what variational Monte Carlo is doing is you write this energy as an expected value, and as an expected value for a random variable that has this density. Then you sample some points with this density, and then you minimize an empirical version of this expected value. For example, and here we are back at neural networks, you can apply stochastic gradient descent and minimize this, just as one usually does. And once one has minimized this, one updates the random variable from which one samples and so on. So that's kind of an algorithm that one can implement. And the first one was by Hahn and others, which did not yet perform comparable to the state of the art, and more recently Hermann and Pfau. So Hermann and Noé from the TU Berlin and Pfau from DeepMind have almost simultaneously found very efficient ways to train these to fit neural networks to minimize this energy. And I would also like to talk about the contribution that we recently had in this direction. Okay, so the reason I want to do this is to highlight the challenges that one faces if one would like to design a neural network algorithm for such a hard problem. I mean, this is really a tough problem. Well, a good thing to do is to look at the existing algorithms that are around. Okay, what is the currently best available numerical representations for wave functions? Okay, and what one usually does is one uses a low rank approach. So one tries to approximate the wave function by products of one-dimensional functions. And as we all know, this can alleviate the curse of dimensionality, right? But we also have this anti-symmetry. So the function has to be anti-symmetric. So usually what you do then is to just collect together all wave functions depending on coordinates of equal spin, and collect them into a matrix and compute the determinant of this matrix. This is called a Slater determinant. And on the one hand, it satisfies the symmetry condition. On the other hand, this tensor product ansatz cannot incorporate many physical phenomena. So basically, this tensor product ansatz would kind of amount to saying that different electrons are independent and do not interact with each other. So what you typically do is you have to take a lot of different Slater determinants with different orbitals. And usually the number of such determinants that you need scales exponentially or even combinatorially in the dimension. And now the trick is, and this is first done in Paulinet, in the work by Hermann and others, and our architecture is called Deep Erwin. It's inspired by that work, is to deform these one electron orbitals by a function. And this function depends on an auxiliary variable. And this is kind of a feature vector that depends on the electron position and on the nuclear positions. Okay, so in order to incorporate interactions between different electrons, we just modify these Slater determinants. Okay, and also enforce other conditions. So singularities, for example, if electrons come close to each other, and so on. So all this has to be enforced in the architecture. And this trick really allows to dramatically reduce the number of free parameters. So if you look at this graph here, so this is from this paper that introduced this Paulinet architecture. It basically compares the number of degrees of freedom or number of determinants that you would need in order to get a certain accuracy. And well, if you would like to have a better accuracy, you need to take more determinants, and then you have the kind of a linear scaling here. And this deep learning architecture here is really an outlier. Okay, and it's with much smaller neural networks, you can represent very complicated wave functions, and this can be used to get highly accurate computations of the ground state energies. And well, this is the architecture. It's kind of a modular architecture which incorporates a method that's a state-of-the-art numerical method, and then deforms basically the output of this method using neural networks. And what we thought is that typically you don't want only one molecular geometry, but you want many, for example, to do molecular dynamics. And so we kind of looked at other machine learning methods, for example, transfer learning, where you share for different similar tasks, you share components of your model. And since we have a modular network architecture, we just shared a certain part, for example, 95% of all parameters across all molecular geometries. And this really gives a dramatic speed up if you want to compute, let's say, a potential energy surface. So it's like a speed up by one order of magnitude, approximately. And well, okay, it allows us also to do other things, like using the shared layers and sharing them not only between different molecular geometries, but between different molecules, also to get some speed up and compute chemical quantities like transition states. Okay, I think that's almost all I wanted to say. I mean, of course, also for high dimensional Black-Scholes PDEs, one can get efficient algorithms using deep learning, and there is a lot of very nice work about this. And this brings me to my conclusion. I think what I really want to say is that, I mean, like all other methods, the deep learning paradigms has pros and cons. Pros, I mean, they are like very flexible, and cons, it's sometimes a bit challenging to realize this flexibility in terms of an algorithm. But what I think is a very important quantity are the sampling numbers. So they provide an important benchmark for the stability of an architecture or a model class. So I think this is really an important avenue for research to classify architectures. The choice of architecture, if we really want to solve a challenging problem, is crucial. And it's usually not possible there to just go and take some vanilla neural network architecture. So it's always a good idea to incorporate existing solvers into this architecture. Okay, I mean, if we have a problem where efficient evaluation is more important than efficient computation, then I mean, one can really benefit from the superior approximation properties of neural networks. And I think all these this gives us a lot of exciting problems, theoretical and computational, that really have a very big potential to advance, for example, computational chemistry, optimal control, and so on. And I'm very excited to do future work in this field. And with this, I would like to close, and I thank you very much for your attention.
Well, thank you very much, Philippe, for a very interesting talk. So if there are questions from the audience, please raise your hand and I can unmute you. I think, Albert, did you have a question?
Yeah, okay. So I have questions, comments actually on the first part of the talk and what you call theory to practice gap. So it's a general feeling that people now are very obsessed and consumed with neural nets. But to me, I mean, this example, what you discussed, in a way, it's a diversion from maybe a more fundamental problem, which is given a class, you are comparing approximability and recovery. Recovery is when you have only a certain amount of information, which are this point value. And for linear approximation, you mentioned result that says it's essentially the same, okay, in a certain sense. And the question is more what goes on now for nonlinear approximation. For so the linear result says that the recovery is what you call the sampling number are bounded by the n width, essentially, the Kolmogorov width. Now you have a similar notion of Kolmogorov width of n width for nonlinear approximation that sort of put in competition fairly general method of approximation. And I think this is the key question. Maybe instead of looking at neural network, isn't that the main question is if you have a certain classes of function, is there a gap between their level of nonlinear approximability as measured by nonlinear width for entropy number, this kind of quantities, and the sampling numbers. Mm-hmm. Because I think, for example, here you consider classes which are the class that can be approximated by neural net. They are very vast class. Maybe you should consider the class that really correspond to your problems. Like what are these PD solutions? This family of PD solutions. Maybe maybe this would be the class to focus on.
But okay, but then I mean, well, thanks for the question. I would just like to point to this result here. I mean, here, all I'm assuming about my class is that somehow a small neural network is embedded in this class. Mm-hmm. Nothing else. So it can be equal to this network architecture, actually. And still, you cannot get a rate better than 2. Mm-hmm. So, I mean, I have to say that this really depends on the rectified linear unit. But it seems to me that, I mean, maybe I don't see some other avenue, but to me it seems like it's really very challenging or impossible to realize high rates with ReLU networks.
or with any nonlinear method. I mean, the problem you mentioned is the same if you were
so let's say
if you were using n-term wavelet approximation or all these methods, all these adaptive methods, if all you are given is n points, because you don't know where the singularity exactly, it's exactly the phenomenon that you are telling, that you can have spikes or things like that.
Right.
That can be very well approximated, but not captured by point value. So all I'm saying is that it's in fact a more it goes beyond neural networks, the problem. It's more
That's
about
true, but still, I mean, let's say nonlinear approximation, you still usually have some embedding results for Bezoff spaces, for example. So for example, if you just raise the Bezoff smoothness, it will not be equal to the, I mean, you can use an embedding result, and at least if you increase the Bezoff smoothness, then also the Gelfand number becomes better. It will not be equal to alpha, but it will depend, it will also grow linearly with alpha. Here, alpha, so the approximation parameter, can grow to infinity, and still basically the Gelfand number does not grow, so the rate of the sampling number does not decay any faster. So it does not go to infinity, it just stays below 1/d. So that's a bit different, I think, even from Bezoff space nonlinear approximation.
Okay, thank you.
Thank you, Albert. So we're running a minute or two late, but if there's another quick question from the audience, we can take that. Okay, not seeing any further questions. Let me thank Philippe again for a very interesting talk. And we will now move on to our second speaker. So thank you, Philippe.
Well, thank you. It was a pleasure. Thanks very much.
Okay, so Sara, you should be able to share your screen. So maybe while you are doing that, I will start with the introduction. So our second speaker today is Sara van der Geer, who's a professor in mathematics at ETH Zurich. Sara's area of research is mathematical statistics with an interest in high-dimensional problems, continuing a theme from the first talk this morning. Areas of focus of her work include empirical processes, curve estimation, machine learning, model selection, and non- and semi-parametric statistics. She's won a series of prestigious awards for her work, and has also been an invited speaker at the ICM in 2010. She's a member of the Academy of Sciences Leopoldina and the International Statistical Institute. She's also a corresponding member of the Royal Netherlands Academy of Arts and Sciences and a fellow of the Institute of Mathematical Statistics and a member of Academia Europaea. She's a former president of the Bernoulli Society and currently serves on the scientific committee for the Mathematical Research Institute at Oberwolfach. So we're delighted to have her here today to give our second talk in this session. So she will talk about the minimum L1 norm interpolator in classification. So please take it away.
Thank you, Ed, very much. Thank you very much for this wonderful introduction. I'm very honored to be able to give a talk here. And so I thank the organizers for giving me this beautiful opportunity to present our work, which is on interpolation. So it's minimum L1 norm interpolation. So the thing we were looking at is that you see that many algorithms achieve zero training error. and still have good test error. So the aim of this talk is to contribute a little bit to understanding this phenomenon. And then we will look at the classification problem and the noisy case. So there is noise, and the only way to get a reasonable test error means that the noise has to be small, because that's the unavoidable error. So that's the base error. So we're going to look at the case where the base error is small. Now let me see if, yeah. So this is the title of the talk. Okay. And these are, so it's joint work with 3 people, Jeffrey Chinot, Felix Kugelmeister, and Matthias Löffler. And Jeffrey and Matthias are postdocs at the ETH, and Felix is a PhD, and they're very bright persons. So most of the work, of course, is due to them. So I'm presenting something which is our joint effort, and if there are errors, they are of course mine. Okay, let's see. So this is more or less the layout. I'm first going to introduce the interpolators that I'll consider in classification. These will be related to 1-bit compressed sensing and to the ADA boost algorithm. And that's about interpolation. And another way to deal with data is to do regularization. So I'm going to look at the high-dimensional case, and so that you can interpolate. But regularization is another route. So just to compare, because maybe some people are a bit more familiar with that, and there I can really show you a proof. And it gives you a benchmark. So otherwise you just see formulas and you don't see where they come from. So after regularization, we go back to interpolation, and then I'll show you some rate of convergence. So it's really theoretical work looking at existing algorithms. So this is the notation. You think of a regression model. So we have a design matrix with covariables or input or whatever, input X. And X is a matrix with n rows and p columns. So you can think of the rows as the individuals and the columns as the variables. And p is much larger than n, so it's a high-dimensional situation where you have more variables than the measurements, so to speak. Then think again of a regression model. There's a vector of unknown coefficients, which I call beta stars. That's a p-dimensional vector, and which is normalized to have L2 norm 1. That sort of makes sense in classification because otherwise the model is not identified. And we think of the sparse situation where the number of non-zero coefficients is small, and we call the number of non-zero coefficients, we call that S for sparsity. Then there's noise, which I call Xi. That's an n-dimensional vector with L2 norm normalized some constant, which I think of this constant square root of, the square root of this, so the normalized L2 norm as the noise level. And we assume that, the usual assumption that the number of unknown parameters divided by sample size, so to speak, is small. So that's the usual assumption for a sparsity. But we'll also deviate from that assumption. And so the notation is the L infinity norm of a vector. That's with an infinity here, the L2 norm, the sum of the squares, and then the square root of that. The L1 norm, the sum of the absolute values. And the L0 norm is just the number of non-zero elements, which is of course not a norm. Okay, so now let's go to the algorithms that I'm going to consider. The first one is you have a sort of a regression model. So you have the regression X beta star plus noise. So linear combination of the columns of the input plus noise. So you have a linear model. And you only observe the sign. Call that Y. And then you interpolate, you want to do classification. So you observe Y and X, and you want to do classification. And the way you do it is you just interpolate the signs. But of course, in high dimensions, there are many ways to interpolate. And the Plan- and Verschienen interpolator minimizes the L1 norm of any interpolator. So you want the interpolator to have the same sign as you observe, the observed sign. So Y is here an n-dimensional vector. And so this is a element-wise equality. And of course, if you only observe the sign, you can multiply any vector by a constant, and the sign does not change if you multiply by a positive constant. So you have to normalize. And the normalization is in L1 norm, empirical L1 norm. So this is the average of the absolute value. So this is interpolating the signs, and then you want to find out how good is this estimator, and that's known, but I want to also show it to have a comparison. And then I want to look at the max margin classifier. So you have the same situation. You observe the sign of the regression function and the input. And then you look at the margin, which is this product Y times XB, and you minimize that. At the minimal value, it wanted to be maximal. So the minimal margin has to be maximal, and you maximize over all vectors with L1 norm less than or equal to 1. So what I'll do later on is I'll just show you how this is related to the ADA boost algorithm, which is a very popular algorithm for classification. Oh, so again, this is an interpolator, right? So you do this sort of requires that the sign of your estimator is the same as the sign that you observed. So you just interpolate the signs. But you require the best interpolation in terms of the maximal margin. Okay, and then the aim is to obtain rates of convergence in L2 for the estimator. And yeah, you see here that indeed there's an identification problem. So I can, without loss of generality, assume that the L2 norm of the unknown vector of coefficients is 1. And then the estimator I also normalize to have L2 norm equal to 1. And then I look at the rate of convergence of that quantity. So, so we're a little bit inspired by the theory on compressed sensing. We just assume that the design is IID Gaussian. So each row of the design is a random variable, which is standard Gaussian, and then these rows are assumed to be independent. This assumption can be relaxed, but then you get just different results. So let's use this somewhat disappointing assumption. Otherwise, just think of it as a start for more complicated situations. Okay, and then to look a bit through the formulas, there's something random going on. We have Gaussian random variables, maybe also the noise is Gaussian. So you get high probability statements, and I write them in this way with the order sign. And sometimes I'll give exact, like exponential probabilities, exponentially small, things like that. Okay, so what is there in the literature for 1-bit compressed sensing? So that's this one, that's this one. This Plan- and Verschienen estimator, that's 1-bit compressed sensing. You may think of the basis pursuit. This is the basis pursuit algorithm, except that you don't observe the regression itself, but you observe only the sign. So the further compression is that you compress to only 1 bit. And the original papers are about the noiseless case. Okay, so we'll look at that, and we'll look at, so there is theory for that. Many papers, mostly also from the line segmentation problem. But for the max margin classifier, I'm not aware of any theoretical results. So that's our main contribution. And that's the one related to ADA boost. So let's just first look at some basic facts. Something I wanted to show you, it's not so important, but still kind of nice. If you look at two vectors, beta and b, so to say, and then take a linear combination of a Gaussian vector, then you get a Gaussian vector with, so one dimensional, it's just again a Gaussian vector with a standard Gaussian vector. But if you look at the expected value of the product of their signs, so the expected value is the arc sign between the arc sign of the inner product between the two vectors. And so that's called Grothendieck identity. And maybe you've seen it. I didn't know it. It's kind of beautiful. And so that's why I show it. But as a corollary, the probability that two vectors give rise to different signs is the arc cosine of this inner product. Yeah, so you can easily see that. You just see that if you have a Gaussian vector, then the distribution is uniform on the circle, and so the probability of being in this having this distance, that's just geodesic distance, that's the arc cosine of the angle. Yeah, so that gives rise to the following. So of course, so if you look at this picture, the geodesic distance, that's this curved distance, is more or less, if you have small distances, the Euclidean distance. Okay. So you can of course see that in a formula. So the geodesic distance is more or less the Euclidean distance between the two vectors, where you use that the inner product, if they both have norm equal to 2, then the inner product is 1 minus 1/2 times the Euclidean distance squared. Yeah, so the Euclidean distance squared, that's the norm squared of those two, which is 1, and then minus twice the inner product. So you get 1/2 times 2 minus the inner product. So that's again the inner product. Okay, so that's the formula. So if you have a Gaussian noise, say we're looking at the population case, not at the sample, but in the population. So you have Gaussian, one random variable with Gaussian distribution with variance sigma squared. And you observe the linear combination plus noise and then the sign. Then the base error is the probability that this noisy sign is equal to the sign of the original regression function. And then you just take this Grothendieck identity and you see that it's more or less equal to the noise level, sigma. So that means that the misclassification error, if you have an arbitrary vector b, not the true vector, not the true regression function, and with the true vector beta star, but some other one, the probability that you make an error, you can just do the Grothendieck identity, and you see it's just like in regression, it decomposes into an approximation error. That's the L2 norm of b minus the true vector, and the noise level sigma squared, just as in regression. So sigma squared is the unavoidable noise due to, that's the base error, or sigma is the base error, and then b minus beta star, if you do estimation, is the estimation error, exactly as in linear regression. Okay, so if we now go to, so now I want to show you a regularized version for this problem. So if you again look at the population, you have some noise with variance sigma squared, the square is outside the bracket I see now. And you observe the sign of the regression function. Well, you don't observe it, this is the population version. Then the expected value of the inner product between this sign and the a linear combination of the elements in X is again this inner product between the true beta star and B. Okay, so if you then evaluate this thing at the true beta star, you get here the inner product of beta star and B, which is 1. So the difference, if you subtract here beta star and put the minus sign, the difference is just the Euclidean distance squared. And there's a constant in front, forget about it. It's just, yeah, the main point is this is just the difference, Euclidean distance between the vector B and the true vector beta star. So if you minimize this over all B, you get exactly beta star. So one way to estimate the unknown coefficient is to replace this theoretical expectation by an average. Okay, so you take a sample and then you take an average and you minimize that. So let's do that. So you take a sample, this is your sample, you take the average. And because of the minus sign, well, you maximize that. And then because it's high dimensional, you regularize with the L1 norm of the solution. And that's just like a lasso. Okay, so the lasso is taking, if you have, you observe really the response variable y, not only its sign, then you can do a least squares regression with a L1 penalty, and that's called the lasso. So that's regularized estimation. Okay, if you now look at this vector, so xi is a p-dimensional vector, and then you take this average, which is an average of p, a large number, p is the number of variables, the average of p variables, and if it's more or less Gaussian, the average of p random variables, their maximum, if you take their maximum, it behaves, well, in our normalization, like square root log p over n. Okay, so that's like a surrogate tuning parameter, which you have to kill by using your penalty. So let me just show you how it works. So if your tuning parameter, here it is, here's your lasso type problem. If your tuning parameter is larger than this surrogate version, then the L2 norm squared of your estimator, the regularized estimator, behaves like important quantity here, the L1 norm of the true regression coefficients times the tuning parameter times a constant. And this tuning parameter is something like square root log p over n, so the rate of convergence is square root log p over n times the L1 norm and times 1 plus the noise level squared. And so there's nothing mysterious, but it's kind of nice to see this result so that you can compare later on. So let's just, to get into it, look a little bit at the proof. So the proof says, okay, the estimator maximizes this average minus the penalty. So it's at least as large as this average at the true function minus the penalty. So if I put the minus sign in front, and if I subtract, so I just reorder this arc-max inequality, I get an arc-min inequality, which looks like this. Okay, now let's look at the Euclidean distance. It's just this population mean. I replace the population mean by the population average. And then I look how far it deviates from the population mean. And then I have to correct for that. Then I use, for this first part, I use the dual norm inequality. So I just say the inner product here can be bounded by the L infinity norm times the L1 norm. And then I'm left with this second term. And for the second term, I use the arc-min result of the previous slide, this one, which is on the slide downstairs. And then I'm done. And then I have a result. Okay, then that's the proof. So there's nothing deep going on here. So if you look back at the result, if you remove the square root here and you put the square root here together, you get something like a rate of convergence, this term to the power 1/4. Okay. Now let's see. Now suppose that the, oh, what's happening? Yeah. Suppose now that the true regression coefficients are sparse. Let the active set be the set where the non-zero coefficients are, and let little s be the size of the active set. Then you can improve the rate. So instead of power 1/4, you get powers 1/2. Now, in view of time, I will not do all the details, but the proof is really not much more complicated. You have to be a little bit more careful with this, with the triangle inequality that we applied. But it's again really very elementary type of result. So let me just go to the next slide to summarize. So the misclassification error of this regularized version is just composed of an approximation error and the unavoidable base error. And you see that the approximation error, which we just more or less proved, behaves like follows. Now you see that if we are in the small noise case, where the noise is very small, less than 1 or bounded, then you can forget about the noise here. It just doesn't change the order of the rate of convergence. So for the approximation error or the estimation error, the rate of convergence is not hurt by having noise. It's only hurt by the fact that you don't observe the regression itself, but only the sign. And so this rate of convergence, if the true vector is only sparse in L1 sense, we call this slow rates. That's from the literature of the lasso. And if it's sparse in the L0 sense, so that's really the usual sparsity, then you get fast rates, an order, a square root order faster rates for the estimation error. So that's our benchmark. Now let's look at our interpolation estimators, which do not regularize but interpolate, namely the Plan and Verschienen interpolator and the max margin interpolator. And to study these, we use results from basis pursuit with noise. So what's a basis pursuit? You observe in basis pursuit, you observe the regression function, not only its sign, but you observe really the noisy regression function. So y is then something else. So you observe y, the regression function, and the input, the design. So you just interpolate the data. And you do it using the interpolator with smallest L1 norm. So why L1 norm? Well, you can also do L2 norm, of course. That's a possibility, but then you'll end up with a huge bias. So that's I would say, not a very nice result. So L1 norm behaves much better. I won't go into details why L2 is not such a good result, but let's look at L1. And so we derived the theoretical results, and then we found out there's a theory for this interpolator in a paper by Wojtaszczyk in 2010. But the proofs we use are a little bit different. And there's also results in a more recent work by Yu, Lin, and Liu for this interpolation problem. But they have some, I don't know, it's up to logarithmic terms, similar results. So that's basis pursuit. Then we will look at this plan- en voorziening estimator, where you only observe the sign of the regression function and do L1 norm minimization subject to a constraint. And we will look at this max margin classification. Okay, that's the program now. Yeah, so far so good. So if you want to study this, you will need, I mean, it will be nice to have good upper bounds for the L1 norm of the estimator. Because once you have a bound for the L1 norm, you know this, the estimator is in some space of coefficients with bounded L1 norm. You can calculate its entropy or Gaussian width or whatever you prefer. And then you can somehow deal with the problem. So we'll briefly explain that also. So let's look at the noisy basis pursuit. So we observe the regression function itself and we interpolate the data and we take the interpolator with smallest L1 norm. And then what is a good bound for the L1 norm of the estimator? So it took us some time to deal with that. So what we first did is look at the dual formulation. And then we can see that the L1 norm of the estimator is bounded by the L1 norm of the true regression coefficients plus a term involving the noise level times square root n over log p. And that follows from the dual formulation and the from the KKT conditions. If you write them, you will see that you can bound this L1 norm by the true L1 norm and then the noise level divided by what? Well, that's something which was kind of complicated. You take the linear combination of let's put it correctly, of the linear combination of the of the columns of X. So that's an n-dimensional vector. And then you take the maximum over that. And then you take the minimum over all possible linear combinations. So if that infimum is large, we're happy because then you divide by it. So then you divide by something large and then there will be something small. Now, so in this infimum involved is the maximum of IID Gaussian random variables, and there are P of them. So lambda here is an n-dimensional vector, and the dimension of X transpose lambda is P. So it's high dimensional. And we know from extreme value theory what is the distribution of the maximum of P random variables if P goes to infinity. But we don't want asymptotics because P is just large, but not going to infinity. So, but still you can sort of see that if the dimension of the problem is high enough, then the whole thing behaves like square root log P as a lower bound. So it's not going to be smaller, it's going to be really square root log P. And that's true. So you really need that your sample size, this is what we need that the sample size is sufficiently small as compared to the dimension of the problem. So we really need a high dimensional situation. And then we see that this infimum behaves like square root log P. And that gives you the result. Okay. So once we have this L1 norm, you can just use it to bound quadratic forms, for instance, uniformly over balls in L1 with some radius m, say. So if you look at this result, you have a vector B with L2 norm equal to 1. So this is an average of Gaussians with variance equal to 1. And then you do it uniformly over this L1 ball. And then what you see appearing is the L1 norm here on the right-hand side. And we're exactly in business because our L1 norm is the inverse, it's square root n over log p. And here it's square root log p over n, and it cancels nicely. So that finally gives the estimation error of our interpolator. So if the dimension is sufficiently large as compared to the sample size, then the error we make is just proportional to the noise level with exponential, so with high probability. So it's very high exponential in n here. So the confidence is very high. And this is true no matter what how the noise was generated. It can be adversarial noise, just can be any noise. So there are no conditions on the noise here. Let me see. So now go to this problem where we only observe the sign and we interpolate the sign using minimizing the L1 norm of the interpolator and normalizations to make sure that it's to normalize, because otherwise it's not identified. Otherwise you can take this minimum arbitrary small. So that's the plan and Verscheen in linear programming approach. And what would be now a good bound for the L1 norm of this estimator? And then what we do is we use this basis pursuit result. So so that looks similar as before. The bound for the L1 norm looks similar as before. And that's just, let's see. So if you take here the true vector, beta star, it will not satisfy the interpolation restriction. So you want a vector here, B, which really interpolates the observed signs. It's not true for beta star, but what we can do, of course, is we can do an interpolation of the noise by something linear. And then we just add that, and then we have a linear combination which interpolates our signs. So let me just make a picture here. So this is the true regression function, and these blue dots or purple dots are the noise. And then we just take some vector B, which interpolates the noise and which has smallest L1 norm. Now we know how that behaves because of the basis pursuit solution. We know how the L1 norm of this new B hat interpolating of the noise behaves. And then if we add that, we have something which interpolates the observed signs, right? So using this noisy basis pursuit result, we have a bound for the L1 norm of the interpolator. Of course, we have to normalize it properly so that it satisfies the restrictions, but that doesn't really hurt much. So that's then it. And once we have this bound, you use some empirical process theory. And so you use this L1 norm to get the bounds on, well, not in this case quadratic forms, but Lipschitz functions. Just a bit technical, but this is then the result. So the L2 norm of the interpolator, after normalizing it so that it is L2 norm is equal to 1, is like a little bit similar like the regularized case, except that instead of that the noise appears like 1 plus sigma, so it's not times this quantity, it appears additive really. So even small noise does not necessarily mean that the estimation error is not suffering. So in the regularized case, small noise means the estimation error doesn't matter, doesn't see it. But for the interpolation, it does see the noise. The rates are otherwise similar. So we have these fast rates, like in the regularized case, if the estimator is, if the regression is sparse. So most non-coefficients are 0. The sparsity is S. And if you just know that the coefficients have a bounded L1 norm, we get the slow rates. But what is also kind of interesting is that instead of a power 1/4, we get a power 1/3. So the power is better than the regularized case. Of course, you can say, okay, then I do a different regularizer, but then you will see you cannot compute it. So it's kind of interesting what's going on here. Yeah, I'll give an overview later. Now, let me just skip this. You can also assume approximate sparsity, but I'll have to look at the time probably. Yeah.
Oh, sorry, you have about 10 or 15 minutes left.
Okay. So let's now go to the max margin classifier. Here's the AdaBoost algorithm. So again, you observe input and the sign of the regression function. And then you do this algorithm. Don't ask me too much, but it consists of iterations. You start in the simplex. Okay, AdaBoost is actually for weak learners, which are learners, so covariables which takes the value plus or minus 1. And we look at Gaussian covariables, so we normalize them to be between plus and minus 1. And so that's the normalization. You start with an initial value for the coefficients and an initial value for the weights, which are in the simplex. Then you look at the direction to go to, so to speak. You take a step size. This step size is inspired by exponential loss, but you can also have other loss functions. Then you update your coefficients with a learning rate, which is called eta. And then you update your weights in the simplex. And after a certain number of steps, t, you stop. So that's a very popular algorithm. It really works in practice quite well, I must say. Yeah. So this algorithm, you can show that if the learning rate goes to 0 and the number of number of iterations goes to infinity, then it goes to the max margin classifier. Yeah, so the margin is y times xb. And you minimize that. You want to have this as large as possible. So that's the same as if you renormalize or rescale. It's the same as looking at the minimal margin. Make sure that it's bigger than 1, and then minimize the L1 norm. The relation between max margin and AdaBoost has been studied in detail in this paper by Liang and Soor, but this is for the case where the number of variables divided by the number of observations goes to a constant, and in our case, it goes to infinity. We look at the high dimensional case. Actually, so I should say that we can show exactly how close the max margin classifier is to the result of the AdaBoost algorithm in terms of the step size, I should say the learning rate and the number of iterations. So we have some exact results for that. I don't expose them here. Okay, so let's look at this minimum L1 norm interpolator this time. And yeah, again, we could look at the KKT conditions, and we did that. And then we get lower bounds for the L1 norm. But let's look at the upper bounds. So the upper bound for the L1 norm is this funny expression here, which is also the lower bound. It's the same. And it has some power 2/3 in it. So how do we get that? We get that again using the basis pursuit result. So the point is, let's see here. If you look at the true regression function, the true regression coefficients, then if you put your beta star in, what you see here is just the absolute value. Think of the noiseless situation. It's just the absolute value of n IID Gaussians. And then you take the minimum of IID Gaussians. And the minimum of IID Gaussians, standard Gaussians, behaves like 1/n. So it's very small. It's never going to be bigger than 1. So the true beta star is never going to solve this problem. Yeah, you can renormalize, of course, but then it will be a very large L1 norm. So the true beta star is not doing anything here. So that was kind of difficult. But what we can do, let's see here. So here you have this red line. Here's the true X beta star. It doesn't stay away from 0. So certainly it's not going to be bigger than 1. But we can sort of trunk it away from 0 at a level, say, epsilon. So now this red truncated function stays away from 0. And then we make a mistake. And in the noiseless setting, say, that's just all there is to it. So we make a mistake. And then we just interpolate this mistake to get a coefficient which stays away from 0. Okay, so this X beta is again a linear combination. It's an interpolator with minimum L1 norm. From the basis pursuit case, we know how its L1 norm behaves of B hat. And then we have a new one, which is staying away from 0, and it has the right sign. And then, of course, it's not bigger than 1, so it's bigger than epsilon. So divide by epsilon, do a trade-off, and that's it. And then you get this bound for the L1 norm, which turns out also to be a lower bound. Well, in order, eh? So this power 2/3 is the correct power. So then, after some work, well, once we have this L1 norm, getting the other results also took us some time. So we have the L1 norm, then you normalize by the L2 norm. So you also have to somehow bound the L2 norm from below, and that also worked. And then once we had that, we were able to prove the slow rate of convergence with the power 1/3. So, but that's the slow rate corresponding to assumptions on the L1 norm. But if you have exact sparsity, we were not able to prove, instead of the 1/3, the 1/2 here. Okay, so let's just look at a little table. So the benchmark is doing a regularization. And then you see that in the L1 sparse case, you get a power 1/4. And we get a power 1/3 if you do interpolation. So that's better. But the noise plays a less pleasant role. Because here, if the noise is small, you can just forget about it. But here, if the noise is small, it can still be playing its role. And L0 sparse for the benchmark, square root for the Plan and Verschiening estimator, square root, and we still stuck with the 1/3 power. And then you can compare it, of course, with the unavoidable base error. Okay, so the conclusion is, well, I should say, so we carried out a lot of simulations, and you see this 1/3 rate occurring for the margin, and yeah, you see the convergence of the ADA boost. You see it really in the simulations, but we see in the simulations also that this 1/3 looks more like 1/2. So apparently we still have some work to do to make the proof better for the exactly sparse case. But it's really kind of so from the simulations, we believe that this 1/3 is also the a lower bound, but we don't have proofs for lower bounds, except for the L1 norm. We have a proof for the lower bound, but not for the L2 norm. So let me conclude. So we see that ADA boost sort of, the max margin has the same rate as the slow rate for 1-bit compressed sensing. However, for 1-bit compressed sensing, we get confidence 1 minus something exponentially small, and for the max margin, the confidence is not so big. And we don't know anything about lower bounds. So if you look at the literature on the line segmentation problem, there are some lower bounds, but they're not directly applicable here. So that's also still an open problem. Right. So let me thank you very much for your attention and for your patience.
Thank you very much, Sara, for a very interesting talk. So we have some time for questions. So if you'd like to ask a question, please raise your hand. Okay, so maybe, oh, we have a hand raised.
No, Sarah, Albert, I was just out of curiosity, but how do you approach lower bound in this kind of, what are the techniques to prove lower bounds? Just to give, I'm completely outside this, but I want to understand, I get an idea of upper bounds, but.
I didn't look at it. I didn't have time, but the lower bounds for the L1 norm, we use this dual norm formulation. There it's kind of okay for the L1 norm. Let's see. How do you prove? Yeah, it's a bit technical question. I don't really know how to answer it. It's not like, the lower bounds like you do with the statistics minimax rates.
No, it's
not like that. It's really the lower bound for something, for an algorithm. Yeah.
I see. No, it's interesting.
Yeah, good question. Do you have an idea how to do it?
Okay.
Thank you, Albert. Other questions? So maybe I can ask my question. So your talk focused on Gaussian design matrices. How far do your results extend to non-Gaussian designs?
So if I go back quickly, No, here. So here you see that what we said to each other, it's all in the log. So we want to divide this thing by log P. If you have a non-independent Gaussian design, we can deal with that. I mean, then you get here a bigger result. But on the other hand, the empirical, so there are two sides to the problem. One is the problem is then less rich. So you get this infimum going to be smaller, but on the other hand, the empirical process part is also less rich. So that cancels probably out. So we can probably deal with it, although it's not so obvious how to do it, because what you need is something like small ball estimates, small ball in the sense of, well, in some sense, there are several small balls estimates around. And then of course you can look at all kinds of kernels and things like that, and eigenvalues and so on. Yeah, for if it's a very spiky design.
Yes, I guess I was wondering about
Yeah.
designs that you see in compressed sensing where you randomly choose, say, rows of a Fourier matrix or some orthogonal
Yeah.
matrix.
Yeah.
So then you have independent rows, but obviously that you don't have independent entries in each row.
Yeah, so it's all in this infamum how to deal with that. Otherwise, there's otherwise there's no everything goes through except for this part here. So I don't know. I know for some cases you can do something, but in general, I wouldn't know. Yeah.
Okay, thank you. We have another question in the chat, so let me unmute.
Hi, Sarah. This
Hi.
is, I have I'm hoping that my question is not too dumb, but in your setting, you are assuming that P should be way larger than N.
Yeah.
Like, what confuses me about this is that, like, let's say that this assumption is not valid in our application. What if I just throw a lot of random features that I already know that they are uncorrelated, like then this satisfies the assumption, but it's kind of fake. But yeah, so that confuses me.
At least I know that something goes wrong in the sense that in our simulations, if we didn't have this, then the whole theory was not visible. You really need P much larger than N also in the simulations. Now your question, it's a good one. It's not a dumb question. Yeah. So it's about interpolation. So you do need enough variables to be able to interpolate. Yeah. I don't know. I again should remain silent here. There should be an easy solution, but it doesn't come to my head now. You just throw in effort. Yeah. So the space should be sufficiently rich. Because if you only have noise, then you don't care about, then it's indeed just throwing in, you can throw extra variables. And if you only have noise, that's fine. And then you get a better result. So you can interpolate better. You can interpolate noise better if you have more variables. Does that make sense?
Right.
It has nothing to do with the beta star.
Right. Yeah, I see what you. So it's kind of the more features, even if they are totally unrelated, that's helping us to kind of capture the noise other than capturing the signal. Maybe
because you have more noise, so you minimize the L1 norm. Right. Suppose you have just exactly P n variables, there's only one solution to the interpolation problem. But if you add more variables, you have more solutions.
Right.
So you can get a smaller L1 norm.
Right.
Yeah, that's, I think.
Thank you.
Oh dear. Yeah.
Thank you. Do we have more questions?
Thank you.
Maybe I can ask one very, very naive question. Is it really desirable to interpolate in these problems, or did you also look at problems where you interpolate approximately, so up to some noise level?
Oh yeah, so that makes the problem completely different. Because what do you mean by up to some noise level? Huh? So if you on average interpolate reasonable well, then you're sort of back in the classical situation. So the reason why we looked at this was just we want to understand this zero training error thing.
Right.
And I don't think there's any advantage, except maybe that this rate of convergence is a little bit surprising, that it's so 1/3 instead of 1/4. But I don't see any advantage, but it's kind of a point of focus nowadays that people try to understand why can zero training error be something useful, and it turns out that it's not completely stupid. Let's put it this way.
Yes.
That you still can have good test error.
Right.
And it also shows you a little bit in the direction. So think of all these algorithms like gradient descent, which is more like a ridge regularization, or maybe in the end L2 interpolation. And this sort of says, okay, some algorithms behave like L1 interpolation, and that's maybe a better thing. So it's just a little contribution to a theoretical understanding of these algorithms. Yeah.
Thank you. And apologies if you heard my puppy in the background there. So I'm not seeing any more questions from the chat. Unless anyone has a final question they'd like to ask. Okay, if not, let me thank Sara again for a very nice talk, and also Philippe for his talk earlier this morning. And thank you to all the audience members for coming to the seminar series today. Let me remind you that the next seminar take place in a month's time. So we hope to see you all there very soon. Okay. Thank you very much.
Thank you.